everybody, my name is Erin and welcome back to my Civil Engineering Handbook. Today's topic is going to apply to engineering hydrology, groundwater hydrology, any hydrology classes. It came up in two of my classes that I can remember. That was my engineering hydrology and then my groundwater system design, which was like a groundwater hydrogeology class. So our water resources and geotechnical civil engineers, I think you might appreciate this one. Those were my 2 points of emphasis in college and I would have found this topic very helpful. So let's get into it. So this incredible topic that we're going to be going over today is called Horton's infiltration model. Now, Horton's infiltration model is important because it tells us about the infiltration capacity of the soil that we're looking at. With this, we can look at how much infiltration will occur during a storm of a certain period, and consequently, we can also figure out how much runoff we're going to have as well. So the governing equation for Horton's infiltration capacity model is as follows. We have FP, I'll define all these variables in a second. FP equals FC plus F naught minus FC e to the negative KT. Now, what are all these variables in this lovely equation we have? This FP is telling us the infiltration capacity at any time t. So that's what this equation is solving for. So we're going to be creating a curve that's telling us what the capacity is of the soil at any time t during a storm, during a rainfall event. And then this FC is our equilibrium infiltration capacity. This is where our infiltration will kind of reach like a plateau where the rate isn't changing anymore. I'll show you what that means in a second. And then our F naught here is our initial infiltration capacity. And then FC, we have that again. And then e to the negative KT, where this K value is representing our rate of decrease. It's a constant that tells us our rate of decrease, essentially. So yeah, that's our governing equation, and let's get into how to use it. We're gonna do so by looking at an example, but we'll get into some conceptual things about the equation as well during this example. So for this example, we're looking at an initial infiltration rate of 125 millimeters per hour, and then an equilibrium infiltration capacity of 15 millimeters per hour. And then we also have our constant K there as well, which is 0.8. So the first question that we're gonna have a good grasp on is what are F naught and FC telling us? Let's draw out a rough sketch of what such a curve would look like, and that'll hopefully give us a better sense of what these numbers are telling us. So on our y-axis, we have the millimeters per hour, which is like that's our infiltration. And on the x-axis, we have our time in hours. And a rough look of what one of these sketches would look like is, it'll look like this, where this very first value here, that's our F naught. That is our initial infiltration capacity, which in our case is 125 millimeters per hour. And then that FC is this value here, where it kind of plateaus. So in this case, we're looking at 15 millimeters per hour. So yeah, if this line is representing our capacity, we're saying that as we move along this way in our time, our capacity, our infiltration capacity, the rate at which the water is able to infiltrate is decreasing. It's getting slower. So it kind of begs the question of why does our infiltration decrease over time? If the soil is still the same soil, why is it taking in water more slowly? An analogy that one of my professors told us was, think of it like a wet paper towel. When you first get a paper towel wet, it soaks up the water really quickly at the start. And then as it gets more damp, it's still gonna soak up some water, but it's not quick anymore. It's slowly, as it gets more water in it, it soaks up water more slowly. And I was like, true. And she said there's friction in the soil that is causing it to slow down. So those two things together really made infiltration and the rate of it kind of click for me. So the friction causes it to slow down. Think wet paper towel. So let's take a look at an example. How much water will infiltrate in this case with the F naught and FC and K values that were given? How much water will infiltrate over an area of 75 square kilometers? We'll look at the first part first, which is a 20 millimeter per hour rainstorm that lasts 6 hours. Now, a constant flow for one period of time is our most simple example of a storm that we could look at. There is not a fluctuation in our millimeters per hour, but we'll take a look at this one for kind of get our heads in how this works. To begin, we will write our governing equation. I really like to draw out kind of a sketch of what we're looking at. So we have our curve here, roughly. I don't know exactly what this curve looks like. And our initial infiltration capacity is going to be up here at 125. And then our equilibrium capacity will be right here where it levels out. And then these are millimeters per hour. And this is our time in hours. And then we have, for 6 hours straight, our 20 millimeters per hour precipitation. So that is just saying this constant rate of 20 millimeters per hour is our precipitation. This is the 6 hour line. Now what this tells us is everything under this curve, everything I'm highlighting in blue, the area under this curve is what's going to tell us how much infiltration we have. When figuring out the area under the curve that you're looking at any time t is whichever value is lower between the Horton infiltration capacity curve and the rainfall. For example, let me draw that out to show you, because that was kind of confusing to me when I first learned this. At this point in time, whatever that time is, the lower value is our rainfall, which is at 20 millimeters per hour. So we have the 20 millimeter per hour right here. And at that same time, our Horton infiltration capacity curve is higher than it. It's up here at whatever this is, 40 or something. So at that given point, you want to take the area under the rainfall curve. In this case, the rainfall curve is smaller up until this point, T. This T that we don't know yet. That point T is where the Horton infiltration capacity model becomes the lower of the two values. Let's try to think about why we do it this way. Let's say this is time 1.5 hours. At this time, our Horton capacity shows us that we're at, what do you think this is? Like 50 millimeters per hour. But our rainfall is only falling at 20 millimeters per hour. We haven't reached that capacity yet. We're not above what our soil can hold yet. The soil can hold more than what it's getting at this point, at this time 1.5 hours. So therefore, the amount that will be infiltrating is everything. But let's move down here to, let's say, 5 hours, and our capacity is below the rainfall, which means we're getting more rainfall than what we can hold at that point. So the amount that will infiltrate is less than the amount of precipitation that we're getting. When this is the case, so all of this time where our rainfall is greater than our infiltration capacity, this area represents our runoff. That area below the rainfall, but above that infiltration capacity at that point. So hopefully that makes more sense. Let's go ahead and solve this problem. When the rainstorm is simple like this, just a constant storm for a certain amount of hours, it's really easy to solve by hand. When it gets more complicated, you can do it by code, and I'll show you how to do that on the next example. You can do it by hand. You can always do it by hand. It's just not fun. So for this, our first step is going to be figuring out when this infiltration curve, FP, equals our precipitation, so equals 20 millimeters per hour. So it's when we're trying to find when our precipitation line, in this case, meets our curve, which is this time t right here. Because it is at that point that we're no longer going to be evaluating the area under the rainfall, but we're going to be evaluating the area underneath the Horton curve. So we'll do 20, which is our FP that we get from right here, equals, and then we're gonna plug in the values from our equation. Our FC is 15, and then plus F naught minus FC, which is 125 minus 15, e to the negative 0.8 t. That negative 0.8 is from our k value, which is 0.8, and then it is negative in the equation. And I'm not gonna solve this by hand for the sake of time, but I believe in you. I believe in you to do it. I've done it before. You end up getting a t equals 3.86 hours. So we learned that in this case, with this rainfall, with this infiltration curve values, we find that the Horton infiltration model equals our precipitation line at t equals 3.86 hours. Now, how do we now get the area on the curve? Hopefully you've all taken calculus at this point, and if not, I don't know how you're in these classes, I commend you. But let's go ahead and integrate. So infiltration is the area under the curve, whichever is lower, the precipitation or the Horton infiltration, from 0 to 6 hours. We can't simply do, oh, our infiltration is 0 to 6 d something dt, because at that time, 3.86 hours, we have to switch over what we're integrating. From hours 0 to 3.86, the curve that we are looking at to integrate under is just that constant rainfall. It's just 20 dt, 20 millimeters per hour. Again, because our capacity is greater than our rainfall, so the soil is able to absorb all of it. But then, for the rest of the time, 3.86 to 6 hours, which is the length of our storm, the total length of our storm, the curve that we're integrating is that Horton curve. So we're looking at this section here. Because now our capacity is less than the precipitation that we're getting, so we're gonna have some runoff. So we integrate, in our case, 15 plus 125 minus 15 e to the negative 0.8 t. Again, I believe in you all to integrate. I'm not gonna do it on here because it's too much time. But I believe in all of us to integrate by hand. Or use an integral calculator, whatever is allowed in your class. But this does become this lovely thing. She's so pretty. Just kidding. I don't love her, but we love her because she gets the job done. And then once we evaluate these integrals over these time periods, again broken up into that first part that's looking under the precipitation and that second part that's looking underneath the infiltration curve, we will get, for that first part, 77.28 millimeters. And then that second part be 37.16 millimeters. And then all together over the entire 6 hours, we're looking at 114.44 millimeters of infiltration. So we have 114 millimeters of infiltration, but what we want to do is evaluate this in that 75 square kilometer area that we were given at the start of the problem. So we want to turn this depth into a volume. Before we do this though, we need to turn our millimeters into kilometers, which is a really disgusting conversion. It's jumping a lot of decimal points, but you find that the conversion, I believe, should be multiplied by 10 to the negative 6. That should get you to kilometers, so we will get a value of 0.0001144 kilometers. And we will get that to a volume of infiltration in that certain area, the 75 square kilometers, by doing the 0.0001144 kilometers times the 75 kilometers squared, which will get us a value of 0.0086 kilometers cubed. And there we have it. That is the volume of infiltration that we will have in this case. Now let's move on over to the computer and I'll show you how to code this, which will get this exact problem done quicker, but it's also really helpful for more complicated rainfall because taking the integral of all these different precipitation values and figuring it can be a lot. So let's hop over to the computer and we'll code it. Okay, so we are gonna be using Google Colab because everybody can have access to it and I just want us to all be in the same little format. Go ahead and name this. So when we're working in our good friend Python, the first thing that we're always gonna wanna do is import numpy as np. And then because we're gonna graph this little guy, we're also gonna need this good classic little friend here. Let's run that, make sure she imports. Start coding or generate with AI, holy cow. We're getting too advanced. So let's first start by defining our variables that we're given. So we know that in this case, our F naught is equal to 125, and this is in millimeters per hour. Our FC is equal to 15 millimeters per hour. And then our K is 0.8. And then let's write out our Horton model. Right here we're using the NumPy E, so that's why you have to do the NP. So there's our equation. That is literally just our Horton equation. That's our governing equation. We know her well. The next thing that I'm gonna do is I'm gonna plot that Horton curve. So what we need to do before we plot is we need to define our T range, what time range we're gonna evaluate. And so I'm gonna create an array. That's just, this is in Python, that's what this function is doing. And we're gonna tell it to go from 0 to 6 in increments of let's do 0.001. In Python, I'm gonna need to send, if we wanted to go all the way to 6, I'm gonna have to set this to one extra step further than 6. So we're looking at steps of 0.001. So we're going from 0 to 6.001. So now when we evaluate it, it will take us all the way to 6. It's just how the indexing works in Python. You need to go one extra. Now that we have that done, we're gonna go ahead and plot it. We're gonna plot our time t versus our infiltration curve, which is the FP that we defined above. And then we'll do an X label, and then we'll label this infiltration. Let's go ahead and we'll run the, hello? Oh, that's so silly of me. I need to define T first because our bestie Horton doesn't know what that is. Okay, let's run that. And then we'll run this. Wow! So that's what our curve looks like. Hello? Why is that there? Anyways, so that is what our curve looks like for this specific case with our initial capacity and our equilibrium capacity. So the next thing that we need to do is we need to plot the precipitation on that same graph. So we're gonna create another array of zeros. We didn't do that last time, but we're gonna do that this time. An array that will have the same shape as our t, so it'll be the same number of whatever it's called. Same amount of things as t we have for p. And so we're gonna, now we wanna fill in that array with the value 20, because in this case, that is the only thing we're working with. So p for t values less than and equal to 6, we're gonna have a p of 20. And in the next more complicated example, I'll show you how we're gonna adjust that for when the precipitation rate is changing. I went ahead and I moved that up to this same little box here so we could get them on the same plot. Now from here we need to figure out where that point is that the curve becomes the lower value between the precipitation and the curve. We need to now figure out where that t value is, where it makes that switch that we were talking about earlier. So we're gonna do index, find where precipitation is less than our FP curve. So what I did here, there might be different ways of doing this, is I made a copy of our Horton curve, that FP that we defined earlier. I made a copy of that and called it infiltration. And then everywhere that our precipitation is less than our capacity curve, I set the capacity curve values, the copy of our capacity curve values, equal to the precipitation values. If that makes sense. Now just for visual sake, I want to highlight what value we're going to be looking at. So what we're going to be doing here is we're going to be filling in, kind of like filling in that area under the curve that we're going to be analyzing for times 0 through 6, looking at this new curve infiltration. And again, this new curve that we just rewrote called infiltration is looking at the precipitation rate up until the Horton curve and precipitation rate equal each other. I'm gonna show the legend. I'm gonna show the plot. Ew! That color is foul. It looks like puke green, but that's okay. Get over it. See how up until that point where they intersect, it's the area under the precipitation, and then after that, it's the area under that Horton curve. So now we're gonna calculate that value by doing integration. We're gonna figure out our time step, dt. It's just gonna be the difference between two time steps. I mean, you could, I'm gonna do it like this, but you could do like 2 and 1 or 3 and 2, and we're just calculating a value for dt. Or you could also do it as dt equals 0.001 because we set it to be 0.001, so I'm just kind of recalculating it, but we know what it is. And then just do a simple total infiltration equals sum of this infiltration curve that we wrote times dt, print total infiltration, I don't know, 2 decimal points? How are we feeling about that? 114.46. That's what we got when we did it by hand. And then let's try to get that to volume of infiltration that we had before. So we know that our area is 75 square kilometers. Our total infiltration, we'll rewrite it. We'll just write over the one that we had previously. Is gonna be total infiltration divided by, divided by 1 to the 6th. And then that will get us from millimeters to kilometers. And then all volume of infiltration will be total infiltration times our area. And then we'll print, let's see. That's what we got when we did it by hand. Now, let me show you if we had the more complicated situation. If we remember, I won't pull it back up because I just won't, but our part B to the example was for the first 3 hours, we have 30 millimeters per hour. And then for the next 3 hours, we have 8-10 millimeters per hour rainstorm. So if we want to adjust that, we'll scroll up here to this part where we define our P array. We'll do P for T less than or equal to 3. We'll set it equal to that 30 millimeters per hour. And then for P T greater than 3, set it equal to that 18. That's so cute. I don't like this example, but those are the values that you get. Let's do 18 for the first 3 hours and then 30 for the next 3 hours. Anyways, you get the picture. You can adjust the precipitation between the hours, and then you can run this code and it'll very easily calculate for you what your infiltration, what your volume is. And you can see how this would be helpful, because if we had like a different, I don't know, if we had a different precipitation every hour and your precipitation curve starts looking like this, you can imagine doing that by hand would be quite irritating. That is all I have for you guys on Horton's infiltration model. I hope it made sense. I hope the code was helpful. I learned how helpful coding could be for this problem when I was in my groundwater hydrology class. She showed us how to do this code, and it was like top tier. It was so helpful. Yeah, I look forward to doing more videos and hopefully help you guys with some more stuff. If you have any specific topics that you would like me to cover, please feel free to comment that. For now, I'm just picking random topics that I don't mind talking about. For now, that is all. I thank you for watching, and I hope you found this helpful. So I'll see you all next time. Bye.